In this video, we study about random vectors and certain operations on random vectors such as expectation, variance and covariance. And then we also see what is the PDF of the combination of two random variables. What is random vector? A random vector is a vector whose elements are random variables. Normally it is written in the form of column vector. We can see it here, x is equal to a column vector of x1, x2 up to xm. So normally a random vector is written in the form of a column vector. Here in this x1, x2 up to xm are random variables. Now this also can be written as x1, x2, xm transpose. A column vector can always be written as the transpose of a row vector. This is convenient to write and saves space. Now expectation of a random vector. We already know how to calculate expectation of single random variables and joint random variables. We've seen them in previous videos. Now expectation of a random vector. Let us write the random vector here. X is equal to, it is written in the fashion of column vector whose elements of random variables. So x1, x2 up to xm, this is a random vector. Now we want expectation of random vector x. So expectation of random vector x is expectation of column vector x. And how we find out? You take mean value of each element of the random vector and arrange them in a column vector. So the expectation of a random vector is a vector of expectation of individual elements. Similarly, suppose if I want to calculate x minus ex, that you want to subtract the expectation of random vector x from the random vector x, then what we have to do? We have to subtract each element of ex from the random variable x. So x1 minus ex1. Similarly, second element x2 minus ex2 and so on up to xm minus exm. So this way we have to calculate expectation and x minus ex. Now we see what is expectation of sum of two random vectors x and y. Now let us write x is equal to a random vector x1, x2 dash dash up to xm. This is a random vector x, and we write a random vector y as y1, y2 up to ym. These are the two given random vectors. Now we want expectation of x plus y. Therefore first we write the sum of random vectors x plus y. We know how to add two random vectors, add individual elements. Then the first element would be x1 plus y1. Second element would be x2 plus y2 and so on. And the last element would be xm plus ym. This is the sum of two random vectors x plus y. Now to calculate expectation of x plus y, take expectation of all individual elements. Then we get expectation of x plus y. So the first element would be expectation of x1 plus y1. Second element would be expectation of x2 plus y2 and so on. And the last element would be expectation of xm plus ym. So this way we are calculating the expectation of random vectors x plus y. Now we compute variance of a random vector. To understand this, I'll write the equation for variance of a single vector, single random variable x. So that we write it here, variance of single random variable x is equal to ex square minus ex whole square. This is for single random variable, mean square minus square of the mean. The same equation, if you extend for a random vector, that is given as variance x is equal to expectation of x into x transpose minus of ex and ex transpose. We know for vectors, the multiplication requires a column vector and a row vector. That is why here x and x transpose in the place of x square and ex and ex transpose in the place of ex whole square. Now, if you imagine that it is a zero mean random vector, then its expected value is 0. Like in a single random variable, if it is a 0 means random vector, random variable, then x is equal to 0. Similarly here, for a 0 mean random vector, expectation of x is equal to 0. Therefore, this equation reduces to expectation of x transpose. Now variance of random variable x, random vector x is equal to expectation of x into x transpose. Now how to compute this? First let us write the random vector x, that is given as x1 x2 dash dash xm. This is random vector x. This has got m rows and one column, so that is m by 1 vector. Now I'll write the row vector. It is x1 x2 dash dash xm. It is one row and m columns, therefore it is 1 by m vector. If you want to multiply this, then it is x transpose. We are multiplying both of them. How to multiply? We know that it will be m by m vector. It is 1 m cross 1 and it is 1 by m, therefore it is m by m vector. So the first element would be x1 square. The second one is x1 into x2. The third one is x1 x3 and so on. It is up to x1 xn. Similarly, the second row would be x2 into x1, x1 x2, and here we have x2 square and we have x2 xn, and so on. The last row would be xm x1 xm x2 dash dash xm square. So this is the product. So now if you want to have expectation of this, so variance of x is equal to expectation of x into x transpose, and if you want to compute that, we know already x into x transpose is this. Take expectation of each element, then you get expectation of x into x transpose. So expectation of each element, if you write it, then the variance x will be computed as the expectation of individual elements of the product of x and x transpose. So ultimately we get this vector. Similarly, covariance of random vector x and y is also calculated as covariance xy is equal to expectation of xy transpose minus expectation of x and expectation of y transpose. In the similar way, we require here x is a column vector, y transpose is a row vector, and as we have done for the variance in the previous slide, similarly we can perform the covariance operation here, except that here x is equal to a column vector x1 x2 up to xm, and let us write y transpose is a row vector written as y1 y2 up to ym. So xy transpose is product of x and y transpose, a column vector with a row vector. So each element of this is multiplied with this. As in the previous slide, we can find out x, y transpose, and then we can calculate expectation of that. Similarly, with the column vector we can find out expectation of x, and with the transpose of y we can find out expectation of y transpose, and by subtracting this component from this we get the covariance. Now why we study random vectors? These vectors are very useful when we deal with Gaussian random processes, Gaussian processes and random processes. Gaussian process is a specific case of a random process. So while we are studying that, these random vectors will come very handy. So far we discussed about random vectors. Now we consider two random variables. This time we are going for two random variables x and y. And let us take z is equal to x plus y. So we are taking the combination of two random variables x plus y. So z is equal to x plus y. Therefore z is also a random variable. So linear combination of two random variable is also a random variable. So z is a random variable. We want to find out the probability density function of z. That is fz z. We want to find out how it is calculated. It can be proved that if two random variables are added x plus y, and then the PDF of x is fxx and PDF of y is f of y. In this case, the resultant random vector z, the PDF of resultant random vector z is given by convolution of the PDF of y with PDF of x. So if x plus y are added, then the resultant PDF is given as convolution of the fxx with f of y. This is very important result to find out the resultant PDF of the combination of two random variables x and y. Previous slide we have seen that if you add two PDFs, then the resultant PDF is given by convolution of individual PDFs. Suppose if you are adding more than two PDFs, what would be the result? I have taken one example here. Suppose you have random variable x, which is a uniformly distributed one, which is looking like a rectangular pulse between 0 and t. And we have three such PDFs. Now, if I add x1 and x2, x1 is a rectangular PDF, similarly x2 is also a rectangular PDF. If I add both of them, we know from signal and systems that if you convolute two rectangular pulses, then we get a triangular pulse like this. So if you take convolution of the rectangular pulses x1 and x2, then the resultant PDF is looking like a triangular one. If we add one more rectangular pulse to this, then the convolution of triangular pulse with a rectangular pulse will be a curve like this, which is closer to Gaussian PDF. It's looking like a Gaussian PDF. So for three summations, we are closer to a Gaussian PDF. If we are adding number of PDFs and taking convolution of number of PDFs, then this resultant PDF will approach to Gaussian PDF. So the important point here is that if you are adding a large number of independent random variables, then the resultant PDF would become Gaussian PDF. In fact, we have very important theorem known as central limit theorem in random variables, which states that the resultant PDF of sum of large number of independent random variables becomes Gaussian PDF. It is a very important observation. If we add a number of PDFs, the resultant PDF would approach Gaussian PDF. And this result very immediately we apply for the noise, because we model noise as Gaussian because noise is a collection of many independent random phenomena. So to understand noise, we use this concept of Gaussian process to understand noise. Now we take summation of two Gaussian random variables. Suppose we take the Gaussian random variable x with mean value mx and variance value sigma x square. This is mean value mx and variance value sigma x square, and the another random variable which is Gaussian is given as y, whose main value is my and whose variance is sigma y square. Now I want to take the resultant PDF of x and y, that is z is equal to x plus y. First of all, what is z? If x and y are Gaussian random variables, the sum of Gaussian random variable or the resultant random variable is also a Gaussian. Then what's about their mean value? The mean value is modified now as mx plus my, and variance value is also modified as sigma x square plus sigma y square. So this is the observation. Suppose if you take a random variable, Gaussian random variable x and a Gaussian random variable y, and the resultant random variable is also Gaussian with a modified mean of mx plus my and with a modified variance of sigma square plus sigma y square. So these are the 3 points here. If z is equal to x plus y, the resultant one is the convolution of these two, which is also a Gaussian. So if linear combination of statistically independent Gaussian random variables is also Gaussian, and its mean value has changed out to mx plus my, and the variance value is changed out to sigma square plus sigma y square. So in this video, we started with random vectors. The concept of random vector is very important in the random processes. So for the random vector, we calculated its expectation. We computed the variance and covariance of a random vector. And then we considered two random variables x and y, and we computed the resultant PDF. So the resultant PDF of any two random variables is given by convolution of individual PDFs. And finally, we consider two Gaussian random variables. If they are added, then the resultant PDF is also Gaussian with the modified mean value of mx plus my and the modified variance value of sigma x square plus sigma y square. We also noted that if we add a large number of random variables, then the resultant PDF is Gaussian, which is stated by central limit theorem.